What if I told you that the same kind of thinking that helps us solve number puzzles also powers encryption, computer graphics, chemistry, and even the structure of symmetry itself? That is the hidden world of abstract algebra, and despite the name, it is not about grinding through endless equations. It is about finding the rules underneath the rules. In this video, we will break down 5 powerful ideas in abstract algebra, why they matter, and how they show up in real life. The first big idea is a group. A group is just a set of objects with an operation that combines them following a few simple rules. That sounds abstract, but here is the key. Groups are the language of symmetry. Think of a square. You can rotate it or flip it in certain ways and it still looks the same. Those moves form a group. Why does that matter? Because symmetry is not just visually pleasing, it helps physicists describe molecules, helps engineers analyze structures, and helps mathematicians understand what stays unchanged when things move or transform. A concrete example, in chemistry, the symmetry of a molecule can help predict how it behaves. Next are rings. A ring is a set where you can usually add and multiply. Integers are the classic example. Why are rings useful? Because they let us study arithmetic in more flexible settings like modular arithmetic where numbers wrap around. That is the math behind clocks. If it is 9 o'clock and you add 5 hours, you get 2 o'clock. That wraparound logic is a ring structure. This is extremely useful in cryptography and computer science, where modular arithmetic helps protect data and make computations efficient. Fields are special rings where division is possible except by 0. So rational numbers, real numbers, and complex numbers are fields. Why do fields matter? Because they are the foundation of algebra, calculus, engineering, and physics. If you want to solve equations cleanly, fields give you the right environment. For example, the equations used in signal processing and digital communication often rely on field-like structures to make calculations reliable and efficient. Now we get to one of the most powerful ideas, homomorphisms. These are maps between algebraic systems that preserve structure. In plain English, they translate one system into another without breaking the important rules. Why is this useful? Because it lets mathematicians simplify hard problems. If two structures behave similarly, a homomorphism can reveal that connection. This is a huge deal in modern math and computer science, where you often want to reduce a complicated problem into a simpler one without losing what matters. Finally, quotient structures. These are made by grouping things that behave as equivalent. The simplest example is clock arithmetic again. Instead of treating 12 and 0 as different, we treat them as the same position on the clock. That creates a new system. This idea is powerful because it lets us compress information and focus on what matters. It appears in coding theory, algebraic geometry, and even in simplifying symmetry problems. So abstract algebra is really about this, understanding patterns, symmetry, and structure at a level deeper than numbers alone. And once you start seeing the world through that lens, you realize a lot of modern math is built on just a few elegant ideas. Abstract Algebra Explained, 5 powerful concepts behind modern math is just one small part of abstract algebra. If you are interested, our full free abstract algebra course is linked in the description.